is the Chapter 15 quiz for Chemistry 122, Spring 2021. Number 1, in this reaction specified acetic acid plus sodamide in equilibrium with the acetate anion and ammonia. The conjugate acid-base pairs are conjugate acids and bases. Those are, identify the acid. That thing that has lost the acid is that material that has lost the hydrogen, that's donated the hydrogen, is your acid. It is your acid. The thing that remains after it's lost the hydrogen is that acid's conjugate base. So here's the acid. CH3COO minus is the acid's conjugate base. So we have acetic acid and the acetate anion as a conjugate acid-base pair. The base, this is the acid, it's reacting with a base. The base is amide. A base is something that receives or accepts the proton. So the NH2, when it receives or accepts a proton, becomes NH3. So NH2 plus a hydrogen becomes NH3. This is the base because it receives the hydrogen. The base receives the hydrogen and forms its conjugate acid. So NH2 minus and NH3 are conjugate acid-base pairs. So the two pairs in this reaction are A, CH3OOH and CH3COO minus. Second acid-base combination pair, conjugate acid-base pair, NH2 and NH3. Conjugate acid-base pairs, they only differ from one another by the presence or the absence of a hydrogen. Number 2, which statements of these about strong acids are true? Strong acids have H atoms bonded to electronegative, all strong acids have H atoms bonded to electronegative oxygen atoms. No, because we have strong acids that don't even have an acid in there, have an oxygen in there, sorry. HCl, HBr, HI. Those are strong acids. They don't have an oxygen there at all. So the first one is not true. Conjugate bases of a strong acid is a strong base itself. As I said in the previous problem, if we take a strong acid, it busts up into H plus and Cl minus. If the Cl minus if the conjugate base of the strong acid Cl had any strength whatsoever, we would draw at least some reverse equilibrium arrow. But we don't do that. We write it only one way. Because if Cl minus acts like a base, picks up a hydrogen, it forms HCl. But what does HCl do? HCl immediately goes back right to produce H plus and Cl minus. So the conjugate bases of strong acids have no tendency to act like a base. Strong acids are very concentrated acids. It has nothing to do with concentration. If I have a 1.0 molar HCl solution, that's a solution of a strong acid. But so is 6.0 molar HCl solution. That is also a strong acid. So a strong acid has nothing to do with the concentration. It has to do with the identity of the acid itself. Strong acids produce solutions with higher pH than weak acids. A higher pH means pH values that are larger than 7, 8, 9. So pH 7.1, 7.2, 7.3, 7.4, 7.5. Strong acid solutions have pH below 2.5. Larger numerical values for pH means the solutions are basic. Strong acids do not produce solutions with higher pH, higher numerical values. Weak acids have pHs about maybe 3, 4, 5. Strong acids all have a pH below 1. So the correct answer here is strong acids are ionized 100% in water. Number 3, what is the OH minus ion concentration of a 5.2 times 10 to the minus 4 molar nitric acid solution? If we do the calculation on this, we are going to be doing the calculation of the concentration of H plus solution, not OH minus. So if we write the reaction, HNO3 in water, or you can write it plus H2O, really doesn't matter. Acid, the HNO3 is your acid, H2O is your base, NO3 minus aqueous, and H3O plus aqueous. How have I drawn the arrow? I've drawn the arrow is not an equilibrium arrow, is an arrow that only goes one way. Since it is a strong acid, if we start out with 5.2 times 10 to the minus 4th molar HNO3, if this goes all the way to the right, we have 5.2 times 10 to the minus 4 molar H3O plus concentration, and we also have 5.2 times 10 to the minus 4 molar NO3 concentration. pH, or excuse me, from various equations, we have shown you H plus OH minus is equal to 1.0 times 10 to the minus 14th. We already know our hydrogen ion concentration. It's 5.2 times 10 to the minus 4th. If we want to solve for OH concentration, we divide both sides by the hydrogen ion concentration. So our hydroxide ion concentration, 1.0 times 10 to the minus 14th divided by 5.2 times 10 to the minus 4th. That is 1.9 times 10 to the minus 11th. Number 4. A 0.1 molar HS solution is 8.4% ionized. Calculate the H plus ion concentration. Let's write the reaction down. HF plus H2O. Do we write the arrow in one direction only, or do we write the equilibrium arrow? We write the equilibrium arrow, or equilibrium arrows. HF acts as an acid, it donates that hydrogen, it becomes F minus and H3O plus. This is an equilibrium situation. This 8.4% ionized percent ionization says how far is a numerical expression of how far to the right that this reaction goes. Mathematically, 8.4% ionization is a concentration of H plus at equilibrium divided by our initial concentration of HF initial, times 100. Do we know what our percent ionization is? Yeah, it's 8.4. If we divide by 100 on both sides, we can get rid of the percent. This is 8.4%. Divide both sides by 100, we get rid of that percentage sign. So we divide both sides by 100 is 0.084. Do we know the initial concentration of our acid? Yeah, it's 0.1 molar. So our initial concentration is 0.1 molar. 0.1 molar. H plus is 0.084 times 0.1 or 8.4 times 10 to the minus 3. So this is H plus 0.084 times 0.1. We move the decimal point one more to the left, 0.0084. That is expressed in scientific notation, 8.4 times 10 to the minus 3. Answer E. Number 5. Calculate the pH of a 6.7 times 10 to the minus 2 molar NaOH solution. When we have NaOH in water, busts up into sodium cations in water, surrounded by a bunch of water molecules, and OH minus 1 anions, hydroxide anions, surrounded by a bunch of water molecules. What kind of base is NaOH? It's a strong base. The group 1, group 2 metal hydroxides are all strong bases, meaning that this reaction only and always goes completely to the right. Notice how I've written the reaction. The arrow only goes one way. So if we start out with 6.72 times 10 to the minus 2 moles of NaOH, initially we have 0 of this, initially we have 0 of that. This goes all the way. After we dissolve it, we have 0 moles of NaOH. We have 6.72 times 10 to the minus 2 moles of sodium cations, and 6.72 times 10 to the minus 2 molar concentration of our OH ions. Two ways we can work this. We can say H plus times OH minus is equal to 1.0 times 10 to the minus 14th. Our OH minus concentration is 6.7 times 10 to the minus 2. H plus times 6.72 times 10 to the minus 2 is equal to 1.0 times 10 to the minus 14th. Solve for H plus, divide 1.0 times 10 to the minus 14th by 6.7 times 10 to the minus 2. We're getting something, H plus is something times 10 to the minus 11th. Excuse me, minus 13th, sorry, minus 13th. Therefore, when we do pH, pH is minus 1 times the log base 10 of our H plus concentration. So it's minus 1 base 10, minus 1 times the log base 10 of whatever this value is times 10 to the minus 13th. So we come up with a pH about 12.83. Or we could do pH plus POH is equal to 14. We have OH. We can calculate the POH as minus 1 times the log base 10 of the OH minus concentration. So it's 6.2 times 10 to the minus 2. This is our pH, since I don't have a calculator. Or, let me see. POH is 1 point something times 10 to the minus, excuse me, 1 point something. 1 point something. We know pOH, we have 14. pH is 14 minus 1 point something. This something should give us the value of 12.83. So solving either way, full credit, as long as you solve it correctly, you'll get full credit solving it either way. Number 6. Predict the direction in which the equilibrium that it will lie. So we mix carbonic acid with sodium fluoride, some hydrogen carbonate, and some HF. Essentially, we're asking which of these is the strongest acid. We have two acids, carbonic acid and HF. Whichever one has the larger Ka value, the smaller exponent, will be the stronger acid. The first ionization constant for carbonic acid is about 4.2 times 10 to the minus 7th. The second ionization is even smaller than that. So in this case, we're only having to look at this first ionization constant. Ka for HF, since it only has one hydrogen to lose, it only has a Ka, one value, 7.4 times 10 to the minus 4th. So of these two, HF is the stronger acid. Since this is a stronger acid than H2CO3, the equilibrium is going to lie to the left. Number 7, what is the pH of a 0.023 molar solution of HCN with a Ka of 4.9 times 10 to the minus 10th? Whenever they're talking about pH, they're talking about how much hydrogen ion concentration. Our Ka value only says it goes from left to right to a certain extent. But that extent, how far it goes, and the concentration of H plus depends upon how much you start with. So let's write the reaction. HCN in equilibrium with H plus and Cn minus. Aqueous, aqueous, aqueous. Equilibrium expression. H plus concentration, Cn minus, over concentration of HCN at equilibrium. Well, at equilibrium, this value numerically is equal to 4.9 times 10 minus 10. Initially, we have 0.023 molar HCN solution. Initially, 0. Before we add the HCN to water, there is no H plus and no Cn minus. After we add it to water, there is a change. Do we know exactly how much? No, we don't. So we let that amount that our HCN decreases be X. What is the ratio between HCN, H plus, and CN? A 1-to-1 molar ratio. How do I know that? Because I wrote the reaction. That's the value of writing this reaction. So as much of the HCN that ionizes, it forms X amount of H and X amount of CN. So this is X and that is X. So at equilibrium, we have 0.023 minus X plus X plus X. Again, pH is the concentration of H plus at equilibrium. We plug these values for this equation at equilibrium. Concentration of H plus times the concentration of CN minus. That is X times X over 0.023 minus X we make the assumption that the amount of X the amount of HCN that decomposes is small, such that we can neglect how big X is. We don't know how big X is, but we're trying to calculate it. But we're saying whatever happens, the amount of HCN that decomposes, or ionizes, I should say, is small. Therefore, we can neglect the X. So if we neglect the X, this becomes 4.9 times 10 to the minus 10th equal X squared over 0.023. We're neglecting the X. We're dropping this X term on the bottom up. Notice we're still leaving it on the top. We still have to calculate how much H plus, or else we can't get to pH. So we multiply this all out. We have 0.023 times 4.9 times 10 to the minus 10th. This value I will call T is equal to X squared. Whatever this value is, 4.9 times 10 to the minus 10th times 0.023, we're calling that the value T is equal to X squared. We take the square root of this value, then we have the value of X. Remember, X represents how much hydrogen ion we have at equilibrium. We do the minus 1 times the log base 10 logarithmic operation on that value. Come out with a pH of about 5.47. The only thing we need to do is confirm, is the size of X really that small such that that is justified? Well, we take the amount of hydrogen ion concentration at equilibrium and we calculate the percent ionization. So 5.47 something times 10 to the minus 6th, and we divide it by our initial solution and we multiply it by 100. Whatever our hydrogen ion concentration is, it's going to be some value times 10 to the minus 6 divided by 0.023. Well, this is going to get us something that is way, 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 way less than 5%. Remember, if you do this calculation and you get to a value of 5%, then the estimation that the amount of X that ionized isn't small. But if it's less than 5% or less, no problem. If no problem, you have no issues with that. This value turns out to be less than 5%. So it turns out that the assumption was correct. Number 8. The pH of a 0.1 pH of a 0.14 molar solution of an unknown monoprotic acid is 5.85. Calculate the Ka of the acid. Okay, again, start out, write your equation. We have an unknown acid, monoprotic acid, Ha. It is in equilibrium with H plus and A minus. The Ka for this expression is H plus over A minus divided by the concentration Ha. In this expression, this is an equilibrium expression. H plus is related to pH. pH is the amount of hydrogen ion concentration at equilibrium. So if we do the inverse log operation of 5.85, we get something times 10 to the minus 6th. Something times 10 to the minus 6th if we do the inverse log operation on 5.85. In our equation, it is a 1 to 1 to 1 mole ratio. So as many moles of Ha ionize, we get that many moles of H plus and that many moles of H minus. So the value of H plus and A minus here are identical to one another. If we create our ice table, initial change at equilibrium, Ha, H plus, A minus, initially it is 0.14 molar. Initially 0, 0. Change, Ha ionizes. So it is minus X. This is plus X. This is plus X. We've calculated what X is. It's the hydrogen ion concentration at some value times 10 to the minus 6. So we know the value of X. So 0.14 minus some number times 10 to the minus 6 is essentially 0.14. 0.14 minus some value that does not start until to the right of the decimal point number 5 is essentially 0.14. So we get our unknown first value here for our H plus concentration times 10 to the minus 6 squared divided by 0.14. That value turns out to be 1.4 times 10 to the minus 5 times 10 to the minus 11. Number 9. Consider the following weak bases and their Kb values. Arrange the conjugate acids of these weak bases in order of increasing acid strength. So as Kb gets numerically larger, i.e. smaller exponents, they become stronger acids. So the bigger the number they have as the exponent, the stronger the acid. Such that Ka times Kb is equal to 1.0 times 10 to the minus 14th. If we know Kb, we can figure out what Ka is. But generally, something times 10 to the minus 10th is going to be, as a base value, is going to be a stronger acid than something that's 1.7 times 10 to the minus 9th. This material that's 5.6 times 10 to the minus 4th is a stronger base than either of these two. But this means that this is going to be a weaker acid. So of these, this is the largest Kb value. The Ka value is small. So of these, this is the weakest conjugate acid. The next strongest is the C5H5NH plus, and the strongest acid here is the C6H7OH. Finally, number 10. Arrange the acids HBr, H2SE, and H3AS in order of increasing acid strength. Weakest on the very far left to strongest on the far right. Any series of elements bonded to an acidic hydrogen, as long as they are neutral compounds, not anions, not cations, neutral compounds. As you go from left to right across any row on your periodic table, the acids become stronger acids. Generally, because as we go from, arsenic to selenium to bromide, we're getting we are changing atomic size. HBr automatically is a strong acid. So this is the strongest acid amongst all of those. As we go from left to right, we decrease size. So arsenic is smaller, As is smaller than selenium. Since, selenium is smaller than arsenic. In this case, we are looking at differences in electronegativity. Selenium is more electronegative than arsenic. Selenium, therefore, wants those electron pairs more than the arsenic does. Therefore, this hydrogen-selenium bond is much more electronegative. Therefore, it is a much more polar bond. The hydrogen lost to selenium is lost much easier than it is to arsenic because arsenic is not as electronegative. So that's why we have this particular order. Hopefully that should help you get some handle on these problems. If you have any questions, please make an appointment to see me during my office hours. Have a good day.